Chapter 10 Gravitation. In chapters 8 and 9, we have learned about the motion of objects and force as the cause of motion. We have learned that a force is needed to change the speed or the direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun. The moon goes around the earth. In all these cases, there must be some force acting on the objects, the planets and on the moon. Isaac Newton could grasp that. The same force is responsible for all this. This force is called the gravitational force. In this chapter, we shall learn about gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational force on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for objects to float in liquids. 10.1 Gravitation. We know that the moon goes around the earth and object when thrown upward reaches a certain height and then falls downwards. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton start thinking. He thought that if the earth can attract an apple, can it not attract the moon? Is the force the same in both cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of its orbit, the moon falls toward the earth instead of going off in a straight line, so it must be attracted by the earth. But we do not really see the moon falling towards the earth. Let us try to understand the motion of the moon by recalling activity. Activity 10.1. Do this. Take a piece of thread, tie a small stone at one end, hold the other end of the thread and whirl it round as shown in figure. Note the motion of the stone. Release the thread. Again, note the direction of motion of the stone. Figure a stone describing a circular path with a velocity of constant magnitude. Before the thread is released, the stone moves in a circular path with a certain speed and changes direction at every point. The change in direction involves change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center. This force is called the centripetal, meaning center-seeking force. In the absence of this force, the stone flies off along a straight line. This straight line will be a tangent to the circular path. More to know. Tangent to a circle. ABC. A straight line that meets the circle at one and only one point is called a tangent to the circle. A straight line ABC is a tangent to the circle at point B. The motion of the moon around the earth is due to the centripetal force. The centripetal force is provided by the force of attraction of the earth. If there were no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Why? According to the third law of motion, the apple does attract the earth, but according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. Equation: the mass of an apple is negligibly small compared to that of the earth. So, we do not see the earth moving towards the apple. Extend the same argument for why the earth does not move towards the moon. In our solar system, all the planets go around the sun. By arguing the same way, we can say that there exists a force between the sun and the planets. From the above facts, Newton concluded that not only does the earth attract an apple and the moon, but all objects in the universe attract each other. This force of attraction between objects is called the gravitational force. 10.1.1 Universal Law of Gravitation. Every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. The force is along the line joining the centers of two objects A, B, D, F equal to g of mm by d square. Figure: the gravitational force between two uniform objects is directed along the line joining their centers. Let us two objects A and B of masses m and m lie at a distance d from each other as shown in figure. Let the force of attraction between two objects be F. According to the universal law of gravitation, the force between two objects is directly proportional to the product of their masses, that is, F proportional m into m, and the force between two objects is inversely proportional to the square of the distance between them, that is, F proportional 1 by d square. Combining equations and we get F proportional m into m by d square, or F equal to g m into m by d square, where g is the constant of proportionality and is called the universal gravitation constant. By multiplying crosswise, equation gives F equal to d square equal to gm into m. Isaac Newton, 1642 to 1727. Isaac Newton was born in Woolsthorpe near Grantham, England. He is generally regarded as the most original and influential theorist in the history of science. He was born in a poor farming family, but he was not good at farming. He was sent to study at Cambridge University in 1661. In 1665, a plague broke out in Cambridge, and so Newton took a year off. It was during this year that the incident of the apple falling on him is said to have occurred. This incident prompted Newton to explore the possibility of connecting gravity with the force that kept the moon in its orbit. This led him to the universal law of gravitation. It is remarkable that many great scientists before him knew of gravity but failed to realize it. Newton formulated the well-known laws of motion. He worked on theories of light and color. He designed an astronomical telescope to carry out astronomical observations. Newton was also a great mathematician. He invented a new branch of mathematics called calculus. He used it to prove that for objects outside a sphere of uniform density, the sphere behaves as if the whole of its mass is concentrated at its center. Newton transformed the structure of physical science with his three laws of motion and the universal law of gravitation. As the keystone of the scientific revolution of the 17th century, Newton's work combined the contribution of Copernicus, Kepler, Galileo, and others into a new powerful synthesis. It is remarkable that, though the gravitational theory could not be verified at that time, there was hardly any doubt about its correctness. This is because Newton based his theory on sound scientific reasoning and backed it with mathematics. This made the theory simple and elegant. These qualities are now recognized as essential requirements of a good scientific theory. How did Newton give the universe square rule? There has always been a great interest in the motion of planets. By the 16th century, a lot of data on the motion of planets had been collected by many astronomers. Based on this data, Johannes Kepler derived three laws which govern the motion of planets. These are called Kepler's laws. These are 1. The orbit of a planet is an ellipse with the Sun as one of the foci, as shown in the figure given below. In this figure, O is the position of the Sun. 2. The line joining the planet and the Sun swept equal area in equal intervals of time. Thus, if the time of travel from A to B is the same as that from C to D, then the areas OAB and OCD are equal. 3. The cube of the mean distance of a planet from the Sun is proportional to the square of its orbital period t, or r cube by t square equal to constant. It is important to note that Kepler could not give a theory to explain the motion of planets. It was Newton who showed that the cause of the planetary motion is the gravitational force that the Sun exerts on them. Newton used the third law of Kepler to calculate the gravitational force of attraction. The gravitational force of the Earth is weakened by distance O, A, B, C, D. A simple argument goes like this. We can assume that the planetary orbits are circular. Suppose the orbital velocity is v and radius of the orbit is r, then the force acting on an orbiting planet is given by F proportional to v square by r. If t denotes the period, then v equal to 2 pi r by t, so that v square proportional r square by t square. We can rewrite this as v square proportional 1 by r into r cube by t square. Since r cube by t square is constant by Kepler's third law, we have v square proportional 1 by r. Combining this with f proportional v square by r, we get f proportional 1 by r square, or g equal to fd square by m into m. The SI unit of G can be obtained by substituting the units of force, distance, and mass in equation as N meter square kilograms to the power kg whole to the power minus 2. The values of G was found out by Henry Cavendish 1731 to 1810 by using a sensitive balance. The accepted value of G is 6.673 into 10 to the power minus 11 nm square kg to the power minus 2. We know that there exists a force of attraction between any two objects. Compute the value of this force between you and your friend sitting close by. Conclude how you do not experience this force. More to know. The law is universal in the sense that it is applicable to all bodies, whether the bodies are big or small, whether they are celestial or terrestrial. Inverse square. Saying that f is inversely proportional to the square of d means, for example, that if d gets bigger by a factor of 6, f becomes 1 by 36 times smaller. Example 10.1. The mass of the earth is 6 into 10 to the power 24 kg and that of the moon is 7.4 into 10 to the power 22 kg. If the distance between the earth and the moon is 3.84 into 10 to the power 5 kilometer, calculate the force exerted by the earth on the moon. Take G equal to 6.7 into 10 to the power minus 11 Newton meter square kilogram to the power minus 2. Solution. The mass of the earth m equal to 6 into 10 to the power 24 kg. The mass of the moon m equal to 7.4 into 10 to the power 22 kg. The distance between the earth and the moon d equal to 3.84 into 10 to the power 5 kilometer equal to 3.84 into 10 to the power 5 into 1000 meter equal to 3.84 into 10 to the power 8 meter. G equal to 6.7 into 10 to the power minus 11 Newton meter square kilogram to the power minus 2. From equation, the force exerted by the earth on the moon is F equal to G of m into m by d square. 6 equal to 6.7 into 10 to the power minus 11 nm square kg to the power minus 2 into 6 into 10 to the power 24 kg into 7.4 into 10 to the power 22 kg by 3.84 into 10 to the power 8 m whole square. 2.02 into 10 to the power 20 Newton. Thus, the force exerted by the earth on the moon is 2.02 into 10 to the power 20 N or Newton. Questions 1, 2. Comment this. Ten point 1.2 Importance of the Universal Law of Gravitation. The universal law of gravitation successfully explains several phenomena which were believed to be unconnected. 1. The force that binds us to the earth. 2. The motion of the moon around the earth. 3. The motion of planets around the sun. And 4. The tides due to the moon and the sun. 10.2 Free fall. Let us try to understand the meaning of free fall by performing this activity. Activity 10.2. Do this. Take a stone, throw it upwards. It reaches a certain height and then it starts falling down. We have learned that the earth attracts objects toward it. This is due to the gravitational force. Whenever objects fall towards the earth under this force alone, we say that the objects are in free fall. Is there any change in the velocity of falling objects? While falling, there is no change in the direction of motion of the object, but due to the earth's attraction, there will be a change in the magnitude of the velocity. Any change in velocity involves acceleration. Whenever an object falls towards the earth, an acceleration is involved. This acceleration is due to the earth's gravitational force. Therefore, this acceleration is called the acceleration due to the gravitational force of the earth or acceleration due to gravity. It is denoted by g. The unit of g is the same as that of acceleration, that is m s to the power minus 2. We know from the second law of motion that force is the product of mass and acceleration. Let the mass of the stone in activity be m. We already know that there is acceleration involved in falling object due to the gravitational force and is denoted by g. Therefore, the magnitude of the gravitational force F will be equal to the product of mass and acceleration due to the gravitational force, that is F equal to mg. From equation, and we have mg equal to g of m into m by d square, or g equal to g of m by d square. where m is the mass of the earth and d is the distance between the object and the earth. Let an object be on or near the surface of the earth. The distance d is equation will be equal to r, the radius of the earth. Thus, for objects on or near the surface of the earth, mg equal to g of m into m by r square, g equal to g of m by r square. The earth is not a perfect sphere. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. For most calculations, we can take g to be more or less constant on or near the earth, but for objects far from the earth, the acceleration due to gravitational force of earth is given by equation 10.2.1. To calculate the value of g. To calculate the value of g, we should put the values of g, m and r in equation, namely universal gravitational constant g equal to 6.7 into 10 to the power minus 11 n m square kilogram to the power minus 2, mass of the earth m equal to 6 into 10 to the power 24 kg and radius of the earth r equal to 6.4 into 10 to the power 6 meter. G equal to g of m by r square equal to 6.7 into 10 to the power minus 11 n m square kg 2 inverse into 6 into 10 to the power 24 kg by 6.4 into 10 to the power 6 m whole square equal to 9.8 meter s to the power 2 inverse, s to the power minus 2 or s2 inverse. Thus, the value of acceleration due to gravity of the earth g equal to 9.8 m s to the power minus 2. Ten point two point two. Motion of objects under the influence of gravitational force of the earth. Let us do an activity to understand whether all objects, hollow or solid, big or small, will fall from a height at the same rate. Activity 10.3. Do this. Take a sheet of paper and a stone, drop them simultaneously from the first floor of a building. Observe whether both of them reach the ground simultaneously. We see that paper reaches the ground little later than the stone. This happens because of air resistance. The air offers resistance due to friction to the motion of the falling objects. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do the experiment in a glass jar from which air has been sucked out, the paper and the stone would fall at the same rate. We know that an object experiences acceleration during free fall from equation. This acceleration experienced by an object is independent of its mass. This means that all objects, hollow or solid, big or small, should fall at the same rate. According to a story, Galileo dropped different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. As g is constant near the earth, all the equations for the uniformly accelerated motion of objects become valid with acceleration a replaced by g. See section. The equations are v equal to u plus at, s equal to ut plus half at square, v square equal to u square plus 2as, where u and v are the initial and final velocities and s is the distance covered in time t. In applying these equations, we will take accelerations a to be positive when it is in the direction of the velocity. That is, in the direction of motion, the acceleration a will be taken as negative when it opposes the motion. Example 10.2. A car falls off a ledge and drops to the ground in 0.5 second. Let g equal to 10 meter second to inverse. For simplifying the calculations, 1. What is its speed on striking the ground? 2. What is its average speed during the 0.5 second? 3. How high is the ledge from the ground? Solution. Time t equal to half second. Initial velocity u equal to 0 meter second inverse. Acceleration due to gravity g equal to 10 meter second to inverse. Acceleration of the car a equal to plus 10 meter second to inverse downward 1. Speed v equal to 80, v equal to 10 meter second to inverse into 0.5 second equal to 5 meter second inverse. 2. Average speed equal to u plus v by 2 equal to 0 meter second inverse to 5 meter second inverse divided by 2, 2.5 meter second inverse. 3. Distance traveled is equal to half 80 square equal to half into 10 meter second 2 inverse into 0.5 second whole square equal to half into 10 meter second inverse into 0.25 second square equal to 1.25 meter. Thus, 1. Its speed on striking the ground equal to 5 meter second inverse. 2. Its average speed during the 0.5 second equal to 2.5 meter second inverse. 3. Height of the ledge from the ground 1.25 meter. Example 10.3. An object is thrown vertically upward and rises to a height of 10 meter. Calculate 1. The velocity with which the object was thrown upwards and 2. The time taken by the object to reach the highest point. Solution. Distance traveled is equal to 10 meter. Final velocity v equal to 0 meter second inverse. Acceleration due to gravity g equal to 9.8 meter second 2 inverse. Acceleration of object a equal to minus 9.8 meter second 2 inverse. Upward motion. 1. B square equal to u square plus 2as. 0 equal to u square plus 2 into minus 9.8 meter second 2 inverse into 10 m minus u square equal to minus 2 into 9.8 into 10 meter square second 2 inverse u equal to root over 196 m second inverse u equal to 14 meter second inverse. 2. B equal to u plus 80. 0 equal to 14 meter second inverse minus 9.8 meter second inverse into t. T equal to 1.43 second. Thus, 1. Initial velocity u equal to 14 meter second inverse and 2. Time taken t equal to 1.43 second. Questions 1, 2. Comment this. (10.3) Mass. We have learned in the previous chapter that the mass of an object is the measure of its inertia. Section. We have also learned that greater the mass, the greater is the inertia. It remains the same whether the object is on the earth, the moon, or even in outer space. Thus, the mass of an object is constant and does not change from place to place. (10.4) Weight. We know that the earth attracts every object with a certain force, and this force depends on the mass m of the object and the acceleration due to the gravity g. the weight of an object is the force with which it is attracted towards the earth. We know that F equal to m into a, that is F equal to m into g. The force of attraction of the earth on an object is known as the weight of the object. It is denoted by W. Substituting the same in equation, we have W equal to m into g. As the weight of an object is the force with which it is attracted towards the earth, the SI unit of weight is the same as that of force, that is Newton, and the weight is a force acting vertically downwards. It has both magnitude and direction. We have learned that the value of g is constant at a given place. Therefore, at a given place, the weight of an object is directly proportional to the mass, say m of the object. That is, W proportional m. It is due to this reason that at a given place, we can use the weight of an object as a measure of its mass. The mass of an object remains the same everywhere, that is, on the earth and on any planet, whereas its weight depends on its location because g depends on location. Ten point 4.1 Weight of an object on the moon. We have learned that the weight of an object on the earth is the force with which the earth attracts the object. In the same way, the weight of an object on the moon is the force with which the moon attracts that object. The mass of the moon is less than that of the earth. Due to this, the moon exerts lesser force of attraction on object. Let the mass of an object be m. Let its weight on the moon be Wm. Let the mass of the moon be mm and its radius be rm. By applying the universal law of gravitation, that weight of the object on the moon will be Wm equal to g mm into m by rm square. Let the weight of the same object on the earth be We. The mass of the earth is m and its radius is r. Table. Celestial body, mass kg, radius m. Earth 5.98 into 10 to the power 24, 6.37 into 10 to the power 6. Moon 7.36 into 10 to the power 22, 1.74 into 10 to the power 6. From equations, and we have We equal to g into m by r square. Substituting the values from table in equations, and we get Wm equal to g of 7.36 into 10 to the power 22 kg into m by 1.74 into 10 to the power 6 m. Wm equal to 2.431 into 10 to the power 10 g into m, and We equal to 1.474 into 10 to the power 11 g into m. Dividing equation by equation, we get Wm by We equal to 2.431 into 10 to the power 10 by 1.474 into 10 to the power 11, or Wm by We equal to 0.165 proportional to 1 by 6. A weight of the object on the moon by weight of the object on the earth equal to 1 by 6. Weight of the object on the moon equal to 1 by 6 into its weight on the earth. Example 10.4. Mass of an object is 10 kg. What is its weight on the earth? Solution. Mass m equal to 10 kg. Acceleration due to gravity g equal to 9.8 meters second 2 inverse. W equal to m into g. W equal to 10 kg into 9.8 meters second 2 inverse equal to 98 Newton. Thus the weight of the object is 98 Newton. Example 10.5. An object weighs 10 Newton when measured on the surface of the earth. What would be its weight when measured on the surface of the moon? Solution. We know weight of the object on the moon equal to 1 by 6 into its weight on the earth, that is Wm equal to We by 6 equal to 10 by 6 N equal to 1.6 Newton. Thus the weight of object on the surface of the moon would be 1.67 Newton. Questions 1, 2, comment this. 10.5 Thrust and pressure. Have you ever wondered why a camel can run in a desert easily? Why an army tank weighing more than 1,000 tons rests upon a continuous chain? Why a truck or a motor bus has much wider tire? Why cutting tools have sharp edges? In order to address these questions and understand the phenomena involved, it helps to introduce the concept of the net force in a particular direction, thrust, and the force per unit area, pressure, acting on the object concerned. Let us try to understand the meanings of thrust and pressure by considering the following situations. Situation 1. You wish to fix a poster on a bulletin board as shown in figure. To do this task, you will have to press drawing pins with your thumb. You apply a force on the surface area of the head of the pin. This force is directed perpendicular to the surface area of the board. This force acts on a smaller area at the tip of the pin. Figure. To fix a poster, drawing pins are pressed with the thumb perpendicular to the board. Situation 2. You stand on loose sand. Your feet go deep into the sand. Now lie down on the sand. You will find that your body will not go that deep in the sand. In both cases, the force exerted on the sand is the weight of your body. You have learned that weight is the force acting vertically downwards. Here, the force is acting perpendicular to the surface of the sand. The force acting on an object perpendicular to the surface is called thrust. When you stand on loose sand, the force, that is, the weight of your body, is acting on an area equal to area of your feet. When you lie down, the same force acts on an area equal to the contact area of your whole body, which is larger than the area of your feet. Thus, the effects of forces of the same magnitude on different areas are different. In the above cases, thrust is the same, but effects are different. Therefore, the effect of thrust depends on the area on which it acts. The effect of thrust on sand is larger while standing than while lying. The thrust on unit area is called pressure. Thus, pressure equal to thrust by area. Substituting the SI unit of thrust and area in equation, we get the SI unit of pressure and Newton per meter square or Newton meter inverse 2. In honors of scientist Blaise Pascal, the SI unit of pressure is called Pascal, denoted as PA. Let us consider a numerical example to understand the effect of thrust acting on different areas. Example 10.6. A block of wood is kept on a tabletop. The mass of wooden block is 5 kg and its dimensions are 40 cm into 20 cm into 10 cm. Find the pressure exerted. Figure A 20 cm, 10 cm, 40 cm, B 40 centimeter, 20 centimeter, 10 centimeter. By the wooden block on the tabletop if it is made to lie on the tabletop with each sides of dimensions A 20 centimeter into 10 centimeter and B 40 centimeter into 20 centimeter. Solution. The mass of the wooden block is 5 kg. The dimensions equal to 40 centimeter into 20 centimeter into 10 centimeter. Here, the weight of the wooden block applies a thrust on the tabletop. That is thrust equal to F equal to M into G equal to 5 kg into 9.8 meter second to inverse equal to 49 Newton. Area of a site, length into breadth, 20 centimeter into 10 centimeter equal to 200 centimeter square equal to 0.02 meter square. From equation, pressure equal to 49 N Newton by 0.02 meter square equal to 2450 Newton meter to inverse. When the block lies on its side of dimensions 40 centimeter into 20 centimeter, it exerts the same thrust. Area equal to length into breadth 40 centimeter into 20 centimeter equal to 800 centimeter square equal to 0.08 meter square. From equation, pressure equal to 49 Newton by 0.08 meter square equal to 612.5 Newton meter to inverse. The pressure exerted by the side 20 centimeter into 10 centimeter is 2450 Newton meter to inverse, and by the side 40 centimeter into 20 centimeter is 612.5 Newton meter to inverse. Thus, the same force acting on a smaller area exerts a larger pressure and a smaller pressure on a larger area. This is the reason why a nail has a pointed tip, knives have sharp edges, and buildings have wide foundation. 10.5.1 Pressure in fluids. All liquids and gases are fluids. A solid exerts pressure on a surface due to its weight. Similarly, fluids have weight and they also exert pressure on the base and walls of the container in which they are enclosed. Pressure exerted in any confined mass of fluid is transmitted undiminished in all directions. 10.5.2 Buoyancy. Have you ever had a swim in a pool and felt lighter? Have you ever drawn water from a well and felt that the bucket of water is heavier when it is out of the water? Have you ever wondered why a ship made of iron and steel does not sink in seawater? But while the same amount of iron and steel in the form of a sheet would sink, this question can be answered by taking buoyancy in consideration. Let us understand the meaning of buoyancy by doing an activity. Activity 10.4. Do this. Take an empty plastic bottle, close the mouth of the bottle with an airtight stopper, put it in a bucket filled with water. You see that the bottle floats. Push the bottle into the water, you feel an upward push. Try to push it further down. You will find it difficult to push deeper and deeper. This indicates that water exerts a force on the bottle in the upward direction. The upward force exerted by the water goes on increasing as the bottle is pushed deeper till it is completely immersed. Now release the bottle, it bounces back to the surface. Does the force due to the gravitational attraction of the earth act on this bottle? If so, why does not the bottle stay immersed in water after it is released? How can you immerse the bottle in water? The force due to the gravitational attraction of the earth acts on the bottle in the downward direction. So the bottle is pulled downwards, but the water exerts an upward force on the bottle. Thus, the bottle is pushed upwards. We have learned that weight of an object is the force due to gravitational attraction of the earth. When the bottle is immersed, the upward force exerted by the water on the bottle is greater than its weight. Therefore, it rises up when released. to keep the bottle completely immersed. The upward force on the bottle due to water must be balanced. This can be achieved by an externally applied force acting downwards. This force must at least be equal to the difference between the upward force and the weight of the bottle. The upward force exerted by the water on the bottle is known as upthrust or buoyant force. In fact, all objects experience a force of buoyancy when they are immersed in a fluid. The magnitude of this buoyant force depends on the density of the fluid. Ten point 5.3 Why objects float or sink when placed on the surface of water? Let us do the following activities to arrive at an answer for the above question. Activity 10.5. Do this. Take a beaker filled with water. Take an iron nail and place it on the surface of the water. Observe what happens. The nail sinks. The force due to the gravitational attraction of the earth on the iron nail pulls it downwards. There is an upthrust of water on the nail which pushes it upwards. But the downward force acting on the nail is greater than the upthrust of water on the nail, so it sinks. Figure. An iron nail sinks and a cork floats when placed on the surface of water. Activity 10.6. Do this. Take a beaker filled with water. Take a piece of cork and an iron nail of equal mass. Place them on the surface of water. Observe what happens. The cork floats while the nail sinks. This happens because of the difference in their densities. The density of a substance is defined as the mass per unit volume. The density of cork is less than the density of water. This means that the upthrust of water on the cork is greater than the weight of the cork, so it floats. Figure. The density of an iron nail is more than the density of water. This means that the upthrust of water on the iron nail is less than the weight of the nail, so it sinks. Therefore, objects of density less than that of a liquid float on the liquid. The objects of density greater than that of a liquid sink in the liquid. Questions 1, 2, 3. Comment this. 10.6 Archimedes Principle. Activity 10.7. Do this. Take a piece of stone and tie it to one end of a rubber string or a spring balance. Suspend the stone by holding the balance or the string as shown in figure A. Note the elongation of the string or the reading on the spring balance due to the weight of the stone. Now slowly dip the stone in the water in a container as shown in figure B. B. Figure A. Observe the elongation of the rubber string due to the weight of a piece of stone suspended from it in air. B. The elongation decreases as the stone is immersed in water. Observe what happens to elongation of the string or the reading on the balance. You will find that the elongation of the string of the reading of the balance decreases as the stone is gradually lowered in the water. However, no further change is observed once the stone gets fully immersed in the water. What do you infer from the decrease in the extension of the string or the reading of the spring balance? We know that the elongation produced in the string or the spring balance is due to the weight of the stone. Since the extension decreases once the stone is lowered in water, it means that some forces acts on the stone is upward direction. As a result, the net force on the string decreases and hence the elongation also decreases. As discussed earlier, this upward force exerted by water is known as the force of buoyancy. What is the magnitude of the buoyant force experienced by a body? Is it the same in all fluids for a given body? Do all bodies in a given fluid experience the same buoyant force? The answer to these questions is contained in Archimedes' Principle, stated as follows. When a body is immersed fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. Now can you explain why a further decrease in the elongation of the string was not observed in activity, as the stone was fully immersed in water? Archimedes. Archimedes was a Greek scientist. He discovered the principle, subsequently named after him, after noticing that the water in a bathtub overflowed when he stepped into it. He ran through the street shouting, "Eureka!" which means "I have got it." This knowledge helped him to determine the purity of the gold in the crown made for the king. His work in the field of geometry and mechanics made him famous. His understanding of levers, pulleys, wheels and axles helped the Greek army in its war with Roman army. Archimedes' principle has many applications. It is used in designing ships and submarines, locomotives, which are used to determine the purity of a sample of milk, and hydrometers used for determining density of liquids are based on this principle. Questions 1, 2. Comment this. 10.7 Relative density. As you know, the density of a substance is defined as mass of a unit volume. The unit of density is kilogram per meter cube, kilogram meter 3 inverse. The density of a given substance under specified conditions remain the same. Therefore, the density of a substance is one of its characteristic properties. It is different for different substances. For example, the density of gold is 19300 kilogram meter 3 inverse, while that of water is 1000 kilogram meter 3 inverse. The density of a given sample of a substance can help us to determine its purity. It is often convenient to express density of a substance in comparison with that of water. The relative density of a substance is the ratio of its density to that of water. Relative density equal to density of substance by density of water. Since the relative density is a ratio of similar quantities, it has no unit. Example 10.7. Relative density of silver is 10.8. The density of water is 10 to the power 3 kilogram meter 3 inverse. What is the density of silver in SI unit? Solution. Relative density of silver equal to 10.8. Relative density equal to density of silver by density of water. Density of silver equal to relative density of silver into density of water equal to 10.8 into 10 to the power 3 kilogram meter 3 inverse. What you have learned. The law of gravitation states that the force of attraction between any two objects is proportional to the product of their masses and inversely proportional to the squares of the distance between them. The law applies to objects anywhere in the universe. Such a law is said to be universal. Gravitation is a weak force unless large masses are involved. The force of gravity decreases with altitude. It also varies on the surface of the earth, decreasing from poles to the equator. The weight of a body is the force with which the earth attracts it. The weight is equal to the product of mass and acceleration due to gravity. The weight may vary from place to place, but the mass stays constant. All objects experience a force of buoyancy when they are immersed in a fluid. Objects having density less than that of the liquid in which they are immersed float on the surface of the liquid. If the density of the object is more than the density of the liquid in which it is immersed, then it sinks in the liquid. Exercises. Do this and comment this.